Hi, everyone. So in the previous lecture, we defined a matroid in terms of its independent sets. So let's just remember for a minute, what is a matroid? Well, for us, it's a finite set and a collection of subsets. And these subsets are what we call independent sets. And they have to satisfy properties that are the same properties that linearly independent sets of vectors have to satisfy. And so just like we have independent sets in a matroid that parallel linearly independent sets in a vector space, we'll also have bases. And we'll see that you can actually define a matroid instead of saying, here's a finite set and here are the independent sets. You can define a matroid by saying, here's a finite set and here are the bases. So let's see what the definition of a basis is. Okay, so if I have a matroid E, a matroid M, and its ground set is E, and I is a collection of subsets of E that we call the independent sets, then we define an element B of I to be a basis if it's a maximal independent set. In other words, it's not a proper subset of any other element of I. Okay. So for example, suppose we have our ground set, the set 1, 2, 3, and our set of independent sets is given here. So 1, 2, 1, 3, and then the singleton sets 1, 2, and 3, and the empty set. So these are the independent sets of a matroid. What are the bases? Well, the maximal ones, right? So the bases are the two sets 1, 2, and 1, 3. And notice that if I wanted to tell you about this matroid, instead of telling you all the independent sets, I could opt to just tell you what the bases are. I could say, listen, the ground set is 1, 2, 3, and my bases are the set 1, 2, and the set 1, 3. And then I'll know those are maximal independent sets. And by property 1 of our definition of matroid, I'll know that all of the subsets of the set 1, 2 have to be independent, and all of the subsets of the set 1, 3 also have to be independent. So specifying the bases of a matroid is more efficient than specifying all of the independent sets. Okay, so the major theorem about bases is the following. So here are the important facts to know. If I have a matroid, all of the bases have to have the same cardinality. That's important. And we define the cardinality of a basis for M to be the rank of a matroid, just like the rank of a matrix. Okay. What else? So if I have two bases, okay, and I take an element little b in capital B, then I can take that element out and find an element of B prime that I can put in. So I get B minus B plus B prime, and that will be a basis. And that's called the basis exchange axiom. So this is basis exchange. And then finally, every independent set is contained in some basis. And that number 3 property is going to be really important when we think about greedy algorithms in a lecture or two from now. Okay, so let's show that all bases have the same cardinality. So let's suppose, let's let B and B prime be bases, and suppose that B prime has larger cardinality than B. Well, since both are independent sets, by axiom 2 of our definition of independent sets, our definition of matroid, since B prime is a larger independent set than B, there exists some element B prime that's in capital B prime, but not in B, such that B plus B prime, so B union B prime is independent. But of course, this is a contradiction because B is strictly contained in B plus B prime, and capital B is supposed to be maximal independent independent set. Okay, so it can't be then that one basis has a larger cardinality than the other. All right, great. All bases have the same cardinality. What else can we show? So let's think about basis exchange. So if I have two bases, I can take an element out of capital B and throw an element from B prime in and get a basis. Okay, so let's let little b be in capital B. Because capital B is independent, every subset has to also be independent. So then capital B minus B is an independent set. Also, we see that it's an independent set and its size is strictly less than the size of capital B. And by part one, we showed that all bases have the same cardinality. So the cardinality of capital B is the same as the cardinality of B prime. Okay, so then I have this set capital B minus B that's an independent set that's smaller than has smaller cardinality than the cardinality of B prime. So by, again, property 2 of the definition of a matroid, there exists a B prime that actually I can take to be in B prime. Oops, I keep doing that, huh? It's in B prime, take away B minus B, okay? Such that B minus B plus B prime is independent. And I can see also that since B minus B prime plus B prime has the same cardinality as B, it must be a basis, okay? Because it can't be, because it's an independent set and it has to be a maximal independent set. It can't be strictly contained in another independent set because all bases have the same size, right? Okay. And then finally, we can build a basis from any independent set. So every independent set is contained in a basis. Let's see why this is true. Let's let I be an independent set, and suppose that I is not suppose it's not a basis. Okay, so then let B be any basis. Well, it must be that since I is an independent set that's not a basis, it must be then that the cardinality of I is less than the cardinality of B. So So then, again, by that same part 2 of our definition of a matroid, there has to exist a little b in capital B, take away I, such that I plus B is independent. If the cardinality of I plus B is still less than the cardinality of B, repeat this, find another element of capital B that's not in I plus B that gives an independent set until we get an independent set of size capital B, and it contains I, so then we're done. That set would have to be a basis. Okay, all done.